Why did you and Mom name me after something that's bad?
Well, we didn't.
Murphy's Law.
Murphy's Law doesn't mean that something bad will happen. What it means is that whatever can happen will happen.
The science fiction genre has captivated audiences since the dawn of cinema over a century ago. But when is the last time you've seen a scientifically meaningful science fiction film? Hundreds of millions go into movie budgets all the time, and frequently, the closest they get to anything scientifically legible is something akin to...
There are over 400 stars in our galaxy. Notice, straight above you, the Hammer of Jeff.
The lines between science fantasy and science fiction are all too often blurred. But the perfect marriage of science and spectacle, one that even furthers the advancement of scientific knowledge, can be found in Christopher Nolan's 2014 sci-fi epic, Interstellar.
All engines look good. Beginning roll program.
A foundational reason for the scientific faithfulness of Interstellar has to do with the fact that an executive producer of this film was Caltech Professor Emeritus of Theoretical Physics, Kip Thorne.
My scientific goal for the coming decade is to watch a black hole be born by studying the gravity waves produced in its violent birth. In this endeavor, I'm working together with an experimental group. They are inventing and constructing a detector for such gravity waves. The observational data from the galaxy M87 suggests that there's a gigantic black hole down in its center. This is really marvelous, because the laws of physics have been telling us for many years that black holes should exist somewhere out there in the distant universe.
He details wonderfully all the science involved with the film in his book, The Science of Interstellar, which was integral for the research of this video. But the origin of Interstellar itself goes back to a failed romance. Okay, maybe a failed romance in Carl Sagan. In 1979, Carl Sagan called up his friend Kip Thorne and set him up on a blind date with an aspiring film producer, Linda Obst.
Carl Sagan, the astrophysicist, a close friend of mine, called me up and said, I want to set you up on a blind date with Linda Obst. She's out here trying to make movies, and she'd like to have a blind date with you. And so, well, the romance didn't really go anywhere, but we became close friends.
It's probably great because we've remained partners and best friends ever since.
And many years later, Linda called me up.
During one of those wait when nothing's happening periods in my career.
Yeah.
And Kip and I had dinner, which we often do. And I said, I'm so bored. I could, I just can't find one fun movie.
And she said, would you like to brainstorm with me for a science fiction movie? And I thought for a few milliseconds, and I said, sure, let's do it.
She wanted to collaborate on a movie concept, one that would involve all sorts of ideas like fifth dimensions, black holes, wormholes, and so much more.
And I said, Kip, tell me, he was working on gravitational waves on LIGO. And I said, if you ever found something on LIGO, what would be the most astonishing discovery that could possibly be made on it? That's how Interstellar began.
They both agreed this couldn't just be a vaguely science-flavored flick, and they were both compelled by the idea that through the lens of wonder, spectacle, and story, moviegoers in future generations could be inspired to scientific learning and future discovery. No matter what, they decided the story would be anchored by two guiding principles. One, nothing in the film would violate the firmly established laws of physics or our firmly established knowledge of the universe. And two, speculation about ill-understood physical laws in the universe will spring from real science, from ideas that at least some respectable scientists regard as possible. These rules already separate this film from most other science fiction films out there. But in order to fulfill this vision, they would need everyone, directors, screenwriters, and producers, to be on board with this vision of respect for science.
And Derek Redmond of Great Britain has pulled up with an injury. Redmond is out.
Of course, this wouldn't be a Nolan film without some sort of bending and tearing of reality, specifically of time in this case.
For me, when I'm up there in hypersleep, or traveling near the speed of light, or near a black hole, time's gonna change for me. planet's gonna run more slowly. Now, when we get back, we're gonna compare.
Christopher told Kip Thorne that he wanted time on Miller's planet to move so slowly that 1 hour there would equal to 7 years back on Earth. Kip was aghast. He didn't think it would be possible for a planet to get so close to a black hole's event horizon without getting sucked in, that its time could move 60,000 times slower than here on Earth.
And I said to Chris, I don't think that's possible. And Chris said, Kip, go do a real calculation and come back and tell me what it says. Because I had been wrong before when I made pronouncements about what was possible and what wasn't, because we had brainstormed together and we had almost always found some way to make his ideas work. So I went home and I rechecked it. This is the shape of the warped space around the black hole. So it's similar to the shape that I showed you for the wormhole. And the color coding is the slowing of time. But the closest Miller's planet can be, if the black hole doesn't spin, is at this location, where it turns out that 1 hour on Miller's planet is 90 minutes back on Earth, and that's nowhere near what Christopher Nolan wanted.
So Kip tried a different approach. What if it was a spinning black hole, something we do observe in space?
And the remarkable thing that I discovered is that if the black hole spins fast enough, then the whirl of space stabilizes the orbit, so you can put Miller's planet very close to the horizon, and 1 hour in 7 years is possible. And so it wasn't the first time, it wasn't the last time that Chris was right and I was wrong in something. He said, go do your homework and come back.
Kip calculated that the spin would have to be 10 to the 14th power of a percentage, less than its destructive maximum spin, in order to work. So it's a pretty unlikely, yet scientifically plausible story decision, especially when considering that it's not as though there are a small handful of potential black holes with which we can compare outcomes. Of all the fertile fields for speculation and storytelling, the expanse of the universe is easily the most vast and fertile, as it is estimated that our Milky Way galaxy alone could carry some 10 million black holes or more, and in the whole universe, the number is estimated at 1 billion, or 10 to the 18th power. While virtually all time travel stories rely solely on fantasy to propel the time travel narrative, Nolan uses science to essentially bring a time travel story to life in ways previously unconceived in cinema. Linda has been networking in Hollywood, and Steven Spielberg is interested in their idea. A week and a half after throwing together a treatment and sending it to Spielberg, Kip picks up the phone.
Hey Kip, it's Linda. Guess what? We got Spielberg.
The search was afoot for a writer, and they settled on Jonathan Nolan, also known as Jonah, the brother and secret weapon of Christopher Nolan. They had collaborated on Batman Begins, The Prestige, and Memento, which was Jonah's brainchild. Jonah was totally on board with the idea of scientific faithfulness. He immersed himself in the science, churning through books recommended by Kip, and meeting frequently to discuss the science and its possibilities as he wrote the script, even offering new ideas for directions in which the science could go.
So he was very committed to making this be scientifically accurate and to understanding the science himself. So I fed him something like 30 or 40 books about geophysics, about planetary sciences, about astrobiology, about relativity and cosmology. And he read these books, devoured them, and then he brainstormed with me.
One of Jonah's ideas for the script involved the blight, which sets the stage for humanity's predicament to start the film.
Blight. Wheat 7 years ago. Okra this year. Now there's just corn. And we're growing more than we ever have. The corn will die.
In that moment, you're seeing a lot of, it was the sort of Bush era in science fiction, misanthropic science fiction. We're doomed, we destroyed the world, and I felt like I was really fed up with watching fiction that concentrated on how bad we were. We screwed everything up. And so wanted to tell a story in which the sort of nameless thing that had happened, we name it a little bit, it's a blight. I just wanted to come up with something that was sort of completely out of, recognizable to us, sort of based on the potato famine, but bigger than us. The idea that, even in calamity, we assign ourselves authorship of it. So, we'll destroy the world. Yeah. We sat down with a bunch of physicists and astrobiologists and spun out all the different ways in which life would be extinguished from this planet, and the vast majority of them had nothing to do with this.
Kip wasn't an expert in this area, and he wasn't about to play fast and loose with the science just for the sake of spectacle. So he assembled a dinner with a team of biological and ecological experts at Caltech. Each weighed in on the possibilities of planetary disaster that could face humanity. Over a few hours, the discussion ran through pathogens, algae blooms, and of course, blight. Such ideas were exchanged that, for instance, 50% of our world's produce is already taken by pathogens, and the once prevalent eastern coastal chestnut tree is now functionally extinct by way of blight. There was the idea of an insect-assisted spread of pathogens, and specialist pathogens that adapt into generalist pathogens, wiping out even more species of plants. At the end of the evening, there was an agreement that, although it was very unlikely, Interstellar's blight and its effect on the Earth's oxygen supply was at least plausible enough to run with. The Interstellar production faced its own seemingly dooming blight after Spielberg announced he had to drop out. The lengthy and intense waiting period to see if the production could recover and find a director began, testing Kip and Linda's faith that this project wouldn't die a slow death in development limbo as Hollywood space junk. Their patience was rewarded when, as Jonah put it, the best possible outcome happened. His brother Christopher Nolan signed on to direct. As a powerhouse duo, they worked in unison to bring the script to the finish line. Filmmaking and science were set to have their most powerful meeting yet.
And once they are together on a project, it just goes like an unstoppable train.
An essential catalyst to this tale is a wormhole which opens up near Saturn and makes the entire interstellar journey possible in the first place. This might be the more scientifically thin concept of the film, but like all the others, it at least finds its basis in scientific speculation. In simple terms, the idea of a wormhole, also referred to as an Einstein-Rosen bridge, is essentially a tube that connects curved spacetime. Kip advises us to think of an apple's exterior being the universe, and the hole through the apple being the wormhole through which an ant could travel, instead of going all the way around the outside of the apple. In order for the walls of the wormhole to not collapse and close off, there must be negative energy threaded inside the walls of a wormhole. Has this negative matter or energy ever been created?
And it is possible to have that kind of stuff, that kind of exotic material, but it's made in very tiny amounts in the laboratory, and usually only for a very brief moment of time. And when I and other physicists have tried to see whether the laws of physics would allow you to hold a wormhole open with that kind of stuff, the equations keep telling us probably not, but they don't give a definitive answer. And the fact that for 25 years, the physicists have struggled to prove that the walls will always collapse and have failed, it gives me some hope that maybe wormholes can exist, can be held open. But I remain dubious, unfortunately. On the other hand, interstellar travel is unbelievably hard by conventional means, and so in Interstellar we use a wormhole.
The most artistic license was taken in turning what would have been theoretically a short and uneventful trip through a wormhole into something a little more dramatic, as Nolan was interested in conveying artistically what such a journey would feel like, not just how it theoretically is. And now we come to the fateful black hole that anchors this tale.
Gargantua, pull us down close to the horizon.
Of all the film spectacles, Gargantua is the mightiest, and the film's most scientifically significant. One might think that in order to create such a dazzling display, science would have to take the back burner in favor of artistic spectacle, but it's not so. Kip worked closely with Paul Franklin, the head of Double Negative Visual Effects House, as well as Oliver James, the chief scientist for Double Negative.
Right in that first conversation, Kip showed me an image of that kind of classical fantasy image of these things and said, this is all wrong. This is not how it is.
Kip provided the equations necessary to create the image, the detail going as far as not only the equations for the trajectories of light rays, but equations that explain how a beam of light's cross-section changes shape and size as it passes in front of the black hole. In a strange reversal of convention, it would be Hollywood providing science and the rest of humanity with the most accurate simulation of a black hole ever produced. Let's break this down. A black hole is essentially warped spacetime, frequently caused by a collapsed star.
In outer space, you can get so much mass together, like in a supermassive star, that the gravity just becomes stronger and stronger and stronger, and eventually the pressure that matter exerts on itself can't keep up. and everything collapses. There's a big explosion. Some of the stuff is blown away, but the rest of it collapses into a black hole.
The pull of gravity is so intensely strong around a black hole that nothing can escape once it enters the event horizon, which is the dark surface of the black hole.
If this were a black hole, then instead of a rubber surface, it would have a surface that is made of absolutely nothing except warped space and time.
Gargantua's mass is 100 million times that of our Sun. Kip calculates that anything less than this, and Gargantua's tidal gravitational forces would tear Miller's planet apart. The extreme warping of space-time around the black hole means that the part of the accretion disk on the back side of the black hole appears to bend under and over it.
When light from the top back face of the accretion disk goes to the IMAX camera, it's bent by that warped space along this path. So the camera thinks that the top back face is up here, so that gives rise to this piece of the image. And the bottom back face, the light rays go down under the black hole and up to the camera. And so the camera thinks the bottom back face is down here. That produces that part of the image.
In addition, Gargantua's accretion disk, made of hot gas, looks relatively flat, which is owed to the fact that the disk is only somewhere in the ballpark of the temperature of the Sun instead of 100 million degrees. This way, Christopher Nolan could be sure that there would still be an impressive display of light, but without the kind of radiation that would fry any human who dared too close. Kip explains that this lack of heat and radiation is possible if the black hole has not torn apart a star in a very long time. Along with this type of inactivity is the possibility of a black hole's magnetic field leaking away, resulting in Gargantua missing the jet one can expect from higher activity black holes. Its brightness and extreme glow can be attributed to Nolan's insistence on the appearance being dictated by how it would appear through the lens of an IMAX camera. But what Kip is most scientifically proud of in the black hole's imagery that previous imagery has missed is its gravitational lensing.
In here you can see things that nobody had ever seen before, and we did publish a paper in a scientific journal called Classical and Quantum Gravity. The camera now is going to orbit around the black hole. The black hole is spinning, but as I told you, there are two images of every star, not just two. It turns out that we see as many as 14 images of an individual star, the same star. And these images are created in pairs and then they annihilate in pairs due to what are called caustics or catastrophes in gravitational lensing. And this is what a camera would see in orbit around a black hole. But this is not what you see in Interstellar. This is what you see in Interstellar. And it's quite different because there's a disk of hot gas orbiting around Gargantua, the black hole, and it's radiating very, very brightly. And the brilliance of that gas emitting light is overwhelming the light from the stars.
Cooper. Come in, Cooper.
Nearly 5 years after the unveiling of Interstellar's black hole, it was revealed that a group of scientists had pulled off the once impossible. They had captured the first ever photo of a black hole. Armed with a system of connected telescopes around the globe, they produced an image of the black hole at the center of the M87 galaxy.
That we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
Unsurprisingly, it bears at least some likeness of Interstellar's depiction. Kip explains the remaining differences in appearance.
Oliver James, who was responsible for this image, said, well, what happens if you take the double negative image for a thin accretion disk and you look at it from above the black hole instead? So we're just going to move the camera from near the equatorial plane up to the North Pole. So if you do that, and then you fuzz things out because the Event Horizon Telescope doesn't have very good resolution, lo and behold,
In 2017, Kip Thorne was awarded the Nobel Prize for his contributions in the LIGO detector, a laser technology that helped him and his colleagues finally detect the gravitational waves of Einstein's theory of relativity for the very first time, as they emitted from the collision of two black holes.
I'm so pleased to see so many of my LIGO Virgo colleagues here. I just want to thank you for making me look so good. I really think of myself as more of an icon for this collaboration, and this Nobel Prize is really something that I accept as representative of you who have made this great success in the end.
After spawning multiple scientific papers, inspiring countless fans to further scientific learning, and its visuals being utilized in university classes around the world, Interstellar's scientific legacy is set in stone. All of this science, vast though it is contained within a story defined by one thing.
Love isn't something we invented. It's observable, powerful. Love is the one thing we're capable of perceiving that transcends dimensions of time and space.
Redmond of Great Britain pulled up with an injury halfway down the back stretch. He's fighting off those trying to help him to finish the race. The applause swelling throughout Olympic Stadium as Redmond, with assistance this time, helped from the track by his dad, Jim.
But our mission, our journey, may not be so different to Cooper's. The stakes never were death. The stakes have always been time, and how we share the little amount that we have. Though not wrapped in the same dramatic package of desperate cosmic exploration, the hero's call to adventure in our own story might just be a little voice from the backyard, or an old voice from the living room, inviting us into a whole other world, to become part of another dimension, the sacred space of memory.